All right, hello everybody. Thank you all for coming to this installment on the stretch code presented by the Boston Building Enclosure Council and the Committee on the Environment. We've got a great presentation here. I know we're all very eager and to learn about the stretch code. And thank you very much to our host, Gil Bain. We outgrew our BSA space, and thank you for the lovely space we have here, as well as our awesome refreshments next door. We got a lot of great events coming up. The Committee on the Environment has been doing a series on the stretch code, and they have their 6th and final installment next Friday, June 16th at 9 a.m. on HERS compliance. So that should be a great follow-up to this presentation as well. We have this.
It's not our final.
Sorry,
It's our final. We will have more. So it is just the next.
The fun just keeps rolling out. We've got a great event with Facades Plus coming to town later this summer. And next, I'd like to introduce our presenters here. We have Andrew Steingard with RDH and Paul Orman with the state. Great team here to talk about the presentation. I'll just hand it over to them. Thanks, guys.
Good afternoon, everyone. How are you? Awesome. Let me make sure I know how this works. Okay. Okay, great. I can get this start. Yeah, I'll just start. Good afternoon. My name's Paul. I work for the Commonwealth of Massachusetts. We're the State Energy Office, the Department of Energy Resources. So I just want to thank everyone for being here. Thank our host, Gil Bain, and the BSA and the different committees. But I want to thank all of you the most because you're the experts that really will help us achieve our building decarbonization objectives, actually requirements. And what I'd like to impress upon you tonight is that building enclosure building professionals have a particularly important role moving forward with decarbonization than maybe you've had in the past. So I just wanted to, okay, let's go here. We've seen that. So in Massachusetts, we actually have a regulation that requires us to reduce our carbon footprint across our whole economy by certain amounts by certain dates. And buildings make up about half of the carbon footprint in Massachusetts. So that means that building design professionals have a particularly important role to play in building decarbonization. Now, building decarbonization is kind of different than just doing energy efficiency. When you're trying to achieve building decarbonization, there's more to do than just reduce overall energy loads of a building. And there's other objectives that we want to achieve: comfort, resilience, simplified HVAC systems. But the most important objective of all, if your mandate is building decarbonization, is to develop a way for you to transition from fossil fuel space heating to electric space heating. So we really have like two really big goals when it comes to decarbonization. One is reducing the energy use of the overall building, but the other is also to enable that transition. So the way that we've been analyzing building efficiency improvements is really no longer sufficient. So let me give an example. This is from a real project. Say you're developing a large office and you're an enthusiastic new, go building enclosure specialist, and you go to the design team and you're asked for your contributions to what can we do to this building to make it better than code. So what you do is you come up with a list from your building enclosure and specialist point of view, and you say, what we should do? We should have a good envelope. Let's make sure we preserve those UAs. Let's have low air infiltration. Let's make sure we take care of thermal bridges. And let's also put in some good ventilation energy recovery as well while we're at it. So that little package you hand to the building energy modeler, and they model things. And what they show for this real life example is that if you do those particular things, the EUI of your office will go from 50 to 47. Is that going to be well received? It's going to be like, I don't know if we really need to do so much of this building enclosure stuff. That's only a 6% improvement. So maybe that's not as high a priority as might otherwise want it to be. So that's the viewpoint of reducing overall EUI, which has been our kind of world for a couple of decades now. But building decarbonization changes everything, because applying these same strategies and taking a look at that building EUI stack, but instead of looking at the total EUI, look at the heating end use portion of the EUI. So on that same building, I only got that teeny little bit of EUI improvement, but look at my space heating improvement. Okay, now it's kind of hard to see because it's only a tiny part of the overall scheme of things. That's why it's like hidden away. So you have to zoom in. And what you find is that when we have good envelope, we have low air infiltration, good thermal bridge mitigation, and we include some good ventilation and recovery. That's kind of the four horsemen of building decarbonization. When we do those things, we can reduce heating end use by 90%. And when we do that, a bunch of really good things happen. One of them is that we don't need as much perimeter heating around our building. Maybe we can eliminate it. That'd be great. We also have more comfort. We also have more resilience. But the thing that really matters is that it's super easy now to go from gas space heating to electric space heating. And very critically important from the standpoint of the Commonwealth of Mass, we look out for all the ratepayers that pay for our grid. We can make that transition without impacting the grid, because if we lower our heating loads this much, we can go from gas to electric and not increase the peak electric load of our building. So I'm pressing upon you today, this is why you see what you see in the current stretch code, is that it is a building decarbonization oriented stretch code. And the things in it are designed to deliver this, to crush heating space use to oblivion. So that way we can transition to electric space heating from gas and fossil fuel space heating without impacting our grid. That's why we're doing what we're doing. All right, so let's take a look through what our code actually has in it. We have 3 levels of code: base, we have stretch, and specialized. Now, base and stretch are based on IECC 2021. Stretch has a bunch of stuff in it that's IECC plus a bunch of building enclosure oriented things, plus good ventilation energy recovery. And then specialized is all those things plus actually delivering the electrification from day one in your building or being electric ready. It also has a requirement for passive house for residential larger than 12,000 square feet, which is cool. So most of the state is already on the stretch code, and that automatically, they get all these updates automatically on 1 July. And then we do have 16 communities already on the specialized. So that's pretty cool. And that list includes Boston, Cambridge, and Somerville, where there's a huge amount of construction going on. So you'll notice that we have a couple of new things in there, and they are oriented towards making sure that your space heating load is really small, that you crushed it to oblivion. So instead of, we don't have just an EUI reduction percent that you're sort of used to. We also have in our new stretch code a thing called the thermal energy demand intensity, affectionately known as the TEDI, T-E-D-I. And that's basically a measure of building heating and cooling demand. So what we're doing is we're asking the design community to focus on heating and cooling demand reduction. Now, all these things look like passive house. So if you're familiar with passive house, what does it require? It requires higher level of air infiltration reduction, thermal bridge mitigation, quality envelope, high level of ventilation and recovery. So our values aren't as strict as passive house, but they're the same criteria because we are barking up the same tree. It's the same trick of requiring of using building enclosure as our first line of defense. Crush the space heating to oblivion. We can basically make space heating almost zero in many buildings. And then we can do all these amazing things with decarbonization. There's a bunch of different pathways. It's a little confusing because we have different needs based on building types and sizes. So if your building is very small, you can follow the prescriptive path. If you're above 20,000 square feet and you're a school, office or residential, then you need to also show that you're meeting these TEDI limits. If you're not one of those, then you can use the regular ASHRAE pathway that you're more familiar with. Now, regardless of which pathway you choose, we do have these mandatory requirements that overlay on top of those things. And the particular ones that are important are the envelope backstop to make sure no matter what happens, we're going to get good envelope performance. To no longer trade away envelope performance for things like lighting improvements, because that's the opposite of what we want to try to do. We want to maintain envelope improvements so that we can crush space heating loads, enable electrification. We also have derating. That's just our way of institutionalizing what ASHRAE and IECC have kind of been missing, which is dealing with thermal bridges and allowing you the rules in the code to preserve good envelope thermal bridge mitigation. So that way it doesn't get VE'd away at the end of the design process. And then we also have air tightness in there that is it's more or less consistent with IECC, the way they were going already, which is great. We also have EV and PV readiness requirements as well. So I'll end with here, and then I'll hand it over to my co-presenter. All these new things of checking that your heating load is below certain thresholds and making sure that your envelope is the mandatory limit and includes the backstops and has the thermal bridge mitigation. These are all things that you can't do as a check at the end of your design process. If you wait till the end to check and you're like, it's just gonna be a disaster. You have to impose your building enclosure knowledge and experience early in the design project and let those requirements be your sort of North Star all the way through and make sure that these things are preserved throughout the whole process. Because at the end, we need to have a building that has very, very low space heating loads so that we can make it electrified without breaking our grid. So thank you to all of you. As I said at the beginning, design professionals in buildings have an important role to play in our state obligations. They're not goals, by the way, they're literally obligations by law for decarbonization. So all building professionals have a role, but building enclosure professionals have a very, very particular elevated importance because of all these reasons. So thank you for helping us on this journey of decarbonization.
Question about heat loads. When you're saying heat loads, are you talking about production of heating or fighting heating?
I don't, can you repeat the question?
You're talking about heat load. Are you talking about production of heat for the building, either occupant comfortable or fighting heating by heating from the occupant to the mechanical?
It's the it's not the heating consumption that's regulated, it's the heating demand that's regulated. So it's the amount of heat that the building wants to have.
The amount of heat delivered to or removed from a space.
Yes,
Yeah.
thank you.
So for commercial building, fighting more cooling, I mean cooling demand than heating demand, or we're forced to cool buildings with heating time, so because we're producing too much heat.
Mhm. Yeah, so you'll see that the heating teddies are very small numbers. We're gonna crush them to oblivion. And then you'll see the cooling teddies are larger numbers, they tend to be 2 digits. And the name of the game of cooling is just to manage cooling. We're not trying to crush cooling to oblivion. You really can't do that. We just don't want cooling to go out of control. So that's why early in the design process, make sure your window apertures and your shading and your solar heating coefficients all make sense to ensure that you don't blow up the cooling as you're addressing the heating. Thank you, Anna.
And we're gonna try to leave a lot of conversation time for the end because I know there's gonna be some spirited discussion here. So as we've had amongst ourselves and with clients and industry leaders, particularly in the glazing industry, it's quite spirited. Thank you, Paul. So Andrew Steingeiser, leading the Passive House Consulting Practice for the Boston office of RDH Building Science. And so I'm quite excited about Passive House being incorporated in the code and so many of the prescriptive requirements looking like Passive House. And we know how to do this. Those of us who've been doing Passive House know how this works. So we're really excited to dig in. So as Paul's trying to say, it's important to make the right decisions early in the design process. The new code requires early phase energy modeling to set targets that need to be followed through the design process. This is the difference. We need to set targets, follow them, and the early modeling allows the greatest opportunity to make changes with the least impact on cost. So we want to be able to set our targets, understand if the design is hitting it, update that modeling throughout the design process. And the traditional time frame of doing a hourly modeling check somewhere late DD to check your ASHRAE compliance as you normally would is too late in the process to have a positive influence on the design. So examples of making the right decisions early involve the architect, the structural engineer, the mechanical engineer, plumbing, enclosure, energy consultant, owner, CM, solid fabricator, you name it. Everyone needs to be at the table to discuss how goals impact each discipline. And speaking of TEDI, so thermal energy demand intensity, TEDI. This is a new metric for us here in Boston. My colleagues from Toronto and Vancouver are quite familiar with it. It's exciting to see it make its way into our codes as well. TEDI works a lot like Passive House and has the same key levers. In our energy consulting, we talk a lot about the key levers in balancing the energy budget. You can pull one, but you may have to compensate with another in balancing the energy budget on the project. And in the updated Massachusetts stretch code, most of these key levers that we talk about have a specific minimum requirement for the Massachusetts amendments. So the building's massing alone can impact how much heat is lost through the envelope before we even touch the energy model. So this can influence TEDI or other energy modeling. Again, even before touching the R value, we can do a lot with that. And more complex shapes or over-articulating the building massing will increase the envelope area compared to the volume. Having an efficient form factor and reducing the envelope area versus the building volume will make it easier to achieve reduced heat loss. So why is this important? Because building massing is something we touch right away, very early in the design process. We are dealing with zoning, FAR, a massing empathetic to the context, perhaps an urban environment. A lot of things go into this, maxing out that footprint to get the program to work. But along with that comes the performance of the building, and pushing and pulling one way has an effect on the energy budget. So with air tightness, we see this appear in the code now too, something familiar to the Passive House community. We have a goal to achieve the modeled air tightness in the actual building, and the energy model is counting on it. The best defense is to carefully detail the enclosure, particularly at transitions between assemblies. Collaboration is necessary between the GC and the design team to make sure all trades that are touching the enclosure are clear on air tightness priorities. And additionally, careful field observation through construction helps catch potential enclosure deficiencies. We see some limits in the code now, 0.35 CFM per square foot of enclosure at 75 pascals. For reference, Passive House at 75 pascals is 0.08 versus 0.35. So it's not quite as stringent as Passive House, but we see it appear. And again, the energy modeling that you do early may ask for a tighter, lower air tightness infiltration rate to get that model to work. So it's important, again, to check the energy model. But again, the minimum requirements there help us towards that goal. And again, it's important to set design targets early with the energy model, and this will also inform the efficiency required with the HRV or ERV, the energy recovery ventilation. So this can be held as a basis of design early in the project if we determine what equipment we need to specify in a project. If the efficiency required proves problematic, another key lever can be pulled somewhere else in balancing the energy budget. So unlike the design of the enclosure, though, there's only so much you can do with the efficiency of ventilation. At some point, it maxes out. So in the code now, there are mandatory ventilation energy recovery for for all but the small ventilation systems. And for most cases, at minimum 70%. That's a little less than we see with passive house, somewhere in the 84-85% range. So with glazing systems, if you choose to use a lot of glazing, it has to perform really well. You may have to be more selective about glazing design priorities. Mullions are the worst performing part. More glass and less mullions within a system will perform better than a system with many mullions. There's currently the 30% max above grade window to wall ratio as a starting point in the code, not including opaque doors and opaque spandrels. And most buildings, assuming that most exceed 30% window wall ratio, will be subject to the enclosure backstop C402.1.5, which we've spent a lot of time looking at lately. And I'm sure everyone here has, in fact. So most buildings will probably be subject to this. And the interesting thing is to note in the window to wall ratio in section 402.4.1, spandrels count as opaque in counting your window to wall ratio, but in the backstop 402.1.5, they count as glazing. So the glazed wall system will include the spandrel in that case. And if you follow the component performance alternative requirements, your glazing should be in a pretty good starting point to comply with, say, your Teddy model or your Ashray model, if that's your path for your project. But of course, that needs to be checked in that particular energy model. The goal is to balance solar heat gain to satisfy both the heating and cooling Teddies, and we see this in the Teddy path, the targeted path, as well as passive house. It's a similar concept to balance heating and cooling. And the heating Teddy limit is likely to be the more challenging target via the Teddy path. Code requires us to be consistent in accounting for gains and losses through enclosure. That includes, in the case of glazing, center of glass, frame, and edge of the IGU. In passive house, we also count the flanking condition, the side install. Now, in all the other code paths, that is accounted for as well. Passive house, we're used to entering that separately in the energy model. In the case of derating the wall, it's just a matter of accounting. That side install goes into derating the R value of the wall. But it's accounted for now regardless of the path. So the goal is to more accurately predict the performance of buildings to make them better. We do this with enclosure performance targets. What is heat flow when enclosure elements are not floating in space? And how do we account for that heat flow? We use points and lines and account for the interface of assemblies. So we start off talking about clear field R value, or U value, which encompasses any repeating elements in the wall assembly, the cladding, attachment, panel joints, through wall flashing, anything in that field of the wall. And then now we're looking at adding to that the thermal bridges that occur in the design as well. So the psi value being those linear thermal bridges, like edge of slab, for instance, if it's shooting through the thermal enclosure, or chi values, the point loads, bridges. So for glazing, the code requires limits on area weighted U values. The code requires now 3D finite analysis for curtain wall spandrel or anything with multi-planar heat flow. This is new to us here. so that there can be large discrepancies between the traditional 2D therm or flexo model and a 3D model. And it's critical particularly for the whole building energy modeling, that there's not an overly optimistic accounting for clear field R value, as there's a risk of a more major delta between modeled and actual whole building energy performance. So it's really important, therefore, to look at the three-dimensional heat flow, as you can see in this spandrel example, where the girts behind the metal panel actually, in this case, bypass the thermal break in the vertical mullions. So, 2D is an acceptable approach when you cut that section, and if you extrude it, everything's the same beyond that cut. But as soon as you have something in a different plane beyond where heat flow is happening, it's going to be less accurately captured and not properly captured with 2D finite analysis. So the code language actually requires this 3D analysis in those instances with multiplanar heat flow. That's an important thing to look at. And the new envelope backstop is simplified from the previous code. It only looks at above grade walls to limit the trade-off with other building enclosure components. The roof and below grade walls are not a part of this equation. High glazed wall systems also must be have interior space heated with an all electric heat pump system. And there's an exception there for highly ventilated buildings in which heat pumps need to be sized for a percentage of the peak heating. So this 3D model here was a case study that we developed that looks like a typical building in Boston, a plus or minus 20-story building with podium, combination of punch window and curtain wall. And this case study assumes a well thermally broken mega panel rain screen wall, utilizing thermally broken clip and rail system. And we can often determine the clear field R value of a thermally broken clip and rail or GERT system from manufacturer's data. They've done the 3D modeling already and published in their product data how much you would derate your clear field R value using that particular product to start with. So already we have a good start at understanding what the clear field R value there is before derating further for other structural thermal bridges or details on the project. And per the code guidelines now, the clear field R value is derated with these different intersections and openings that occur. In this case, an R23 wall becomes R14 or so when it is derated. And in this case, this is using a particular tool that you can go access and find for free on the BC Hydro website. And I believe BC Hydro is also referenced in some of the code guidance as well, where you can go in and enter your clear field R value and then the other thermal bridges to quickly evaluate at a high level your clear field R value derated. So that would be the first step is accounting for those different bridges, that roof to wall connection, outside corners, all the window openings, similarly curtain wall openings. In this case, a canopy is counted as a series of point connections, given that it's probably like a knife plate detail through the thermal boundary. And more insulation can be added to the wall here, or thermal bridging can be mitigated in some place like the window openings. If you look in the chart here, 16% you see highlighted in the red box. This tells us that the majority of the heat flow in our thermal bridging is actually through the window openings. So if we wanted to, we could target that particular detail and look to mitigate that thermal bridging if we wanted to improve our clear field R value, in addition to simply adding more insulation. And to obtain thermal transmittance values to plug into that spreadsheet tool, you can also find a catalog of them at thermalenvelope.ca. This is also referenced in the guidance documents that DOER has. you can find an assembly that is very close and for instance, that SI install the flanking condition for the edge of the glazing detail. It offers you a 3D modeled, pre-modeled range of transmittance rates. So you can take that table, you can take transmittance values you find cataloged, and you can put them together and start to derate of some level of accuracy the vertical enclosure. So, and here's an example of then taking it to the next step where you do the weighted U value table for section 402.1.5. This example just passes. We see that derated R value of 14.4 there. That started out as more nominally close to 23, 24. And the code cuts some slack for higher percentage glazing buildings. Buildings more than 50% glazing, the limit of U 0.1285 is raised to 0.1600. Now, this seems counterintuitive, right? Why would you have more flexibility if you're glazing the building more? But a project can't simply increase its percentage of glazing to sneak under that raised limit, say 50, 51%, without ramifications to this weighted U value table. Increasing the percentage of glazing obviously increases the amount of area of higher U value material, and it also increases the linear feet of that flanking condition, SI install. So you're also increasing your heat loss there. So the goal here is to still allow the use of curtain wall, as we understand it, but achieve exterior wall R values that provide interior surface temperatures and thermal comfort to allow the elimination of perimeter space heating like Passive House does. So that's kind of the goal, and that's where those numbers come from. I asked Paul this question because it seemed kind of random. Where's 0.16 come from? Well, it's to attempt to eliminate that space heating at the perimeter. So those same flanking conditions highlighted in this case study can be modeled too. You can look at a similar condition that's cataloged in thermalenvelope.ca, or you could actually do, in this case, a 2D model. It can be more accurate than the database of information because you're getting into project specifics at this point. And when mitigating the thermal bridging at the window perimeter by over-insulating the frame, we can achieve a lower transmittance value. So on the left is the starting point window in the rough opening. On the right, we're taking the exterior mineral wool in this case and bringing it up and over-insulating the frame like we do in Passive House oftentimes. If you take that lower SI install value, plug it back into that same thermal bridging spreadsheet tool, you can see that it is equivalent to adding 1 to 2 inches of insulation to the wall itself by mitigating that thermal bridge of the flanking condition. So this means if you're not hitting the backstop, mitigating that thermal bridging at the window opening could help bring it into compliance even before adding insulation to the wall. Or if you are hitting the backstop and you mitigate that thermal bridging at the opening, you could possibly reduce the amount of wall insulation in the entire wall, which does what? It lets you have a thinner wall section, potentially more rentable floor area. So this is why it's important to evaluate all these conditions together. And these are the kinds of studies that we should be doing as early as possible also, and it has an impact on cost estimating. So I think we have a number of conclusions. Some of these are yours. You'll recognize the language in some of them. Okay. So, we talked a little bit about absolute metrics versus the percentage better than approach that we've seen in past code cycles. So that move to absolute metrics initiates meaningful carbon emissions reduction, as Paul was looking at with when you zoom into the Teddy and you see a 90% reduction, you know, when you look at something like Teddy or Passive House, you're in the next point, crushing the space heating loads to oblivion. And I've heard Katrin say that before too,
She got that.
crushing space heating loads to oblivion. I don't know when Katrin became Arnold, but so you share that, I guess. But as Paul likes to point out, it allows us to switch from gas to electric with minimal impact on the grid, which is really important because obviously development needs to happen on the grid scale at the same time as ongoing electrification, but we can't simply just switch everything to be electric without focusing on demand reduction first, which is the whole point. So the code limits the quantities of poor performing vertical enclosure assemblies as well. And curtain wall is going to have to be used more selectively until the point at which some innovation occurs in the industry, which is no small task. You know, improved thermal performance is required. Otherwise, may not see 100% curtain wall building anymore. And I know that's shocking. I'm an architect. That hurts a little, but you know, all the above reasons, you know. So designers may not realize what's coming with that enclosure backstop. You know, this might mean triple glazed IGUs, warm edge spacers, argon, pretty standardly just to hit the backstop. So again, 2D finite analysis to evaluate the rating can be iffy in some situations. We're trying to account honestly, and so again, the accounting in the design phase is really important too. So we right size mechanical systems, close that performance gap in actual versus modeled performance. And as Paul said, building enclosure designers are now the first line of defense in decarbonization. I'd expand that to architects as well, because you know, you're in there first, and you hold the keys here, and so it's really important to start looking at all these things in combination from early on in the project. And as Paul's pointed out as well, the state is placing a big bet on design teams, and it will pay off because heating loads are going to allow us to electrify and move towards overall building emissions reductions. So let's end it there. And I know you'll have a lot of questions. Certainly.
Oh, yeah, I think at the beginning, sorry, I didn't know how to do that.
Okay.
There's just Q&A. So when we're done, and then we'll move to Q&A.
Okay. Is someone monitoring that, or should we look at that?
I think if you want to do room questions first, you can pull those up.
Okay.
When buildings now submit for a permit, what drawings should architects be producing from an enclosure perspective to meet all of these requirements? Is it kind of a 3D analysis for every, for every wall type? Is it, what should it look like? I'm working with a number of project teams that kind of are scrambling, and they kind of are looking to understand how to get this level of performance into the design, but we've never documented it or had to document it for ISD submission, for example, in the city of Boston.
So I'll repeat the question in case it was hard to hear. The question was, what documentation is required to show the thermal bridge compliance? Actually, so are you able to go to your slide that shows the BC Hydro table?
Sure. I can skip back over here. Sorry, it's at the end. This one?
Should be, no, keep going. This is what is that one? Yep, one more, go back. So the fundamental documentation for compliance demonstration would look like this. So it would have a connection to the different areas and clear field and linear, et cetera, with a kind of a row spreadsheet approach, column showing what the values you chose were. And then you should have a connection to show where you got the value from. So I would hope that most designers would go to the BC Hydro resource. So if you go to the next slide. The BC Hydro resource is amazing. It has a lot of details that have no mitigation to like crazy mitigation and everything in between. So that way you can go there and, look to see what makes sense for your project. And then as Andrew was saying, there might be one particular kind of linear, for example, that's most of your thermal loss. So maybe you target that one for the high level. But your submission would include then, a little screenshot showing that that's where you got it from, so that the ISD would see that that's what you're representing as your detail. And then if it was the case, so the code allows you 3 ways to show compliance with thermal bridging. One is the BC Hydro database. The other is default deratings, which are very punishing. So use them sparingly because they assume that you're not doing any mitigation. But there might be some places where it's not a big deal. It's not a big part of the overall numbers. So you just do that. So you would just have you in your sheet showing that it was made default. And then the other way, if it truly can't find what you're trying to do, then you have to model it. So then you might have the output of that model as part of your submission. But I would hope that most projects don't have to model anything. If it is the case that there's something that just plain doesn't exist in BC Hydro that is really important and common, tell us about it and let's work together, get it modeled and get it in the BC Hydro database. So that way we can kind of continue to learn from each other. Good question.
If we decide to model, instead of those other options, and we no longer have a side value, the derating is hooked into that model, if you want to think about it that way, how would you expect us to submit that? Would you like an account package to show how that system was derated? Would that be part of the submission?
Yeah, like if you're modeling the opaque portion of a curtain wall, that you're not going to really boil your results down to a side value. You're going to boil it down to kind of the overall heat loss of the whole piece. So then, yeah, it would be just what you described. We can do spirited conversations too, because I'm sure there's some concerns.
Maybe
Yes,
some
sir.
online.
Construction is moving a lot towards unitized wall, mega panel. So derating those panels are extremely difficult right now. Not sure if the industry is ready for that stretch code approach of using unitized wall, which are the wall itself can be over insulated, but we're just putting in a lot of zippers. Very well insulated sleeping bag, as I call it. So how do you mitigate that approach? Right now in my office, we're trying to insulate the zipper. Even insulating the zipper is not enough.
Well, you have to account for things honestly, and you have to meet the standards. So yeah, it's going to take some work to make it work.
The panelized example is a challenge because most high-rise projects want to be panelized, right?
Yeah.
In one way or another. And there are limited solutions on the market, right? So,
Even lower, like high level.
mhm.
Highly incentivized to unitize panel.
Yeah,
Either building, higher quality of building inside environment and delivery on site, and then it's quick.
yeah. Yeah, we have a number of projects currently that are panelized and exploring different options. And it really comes down to the detailing, being really careful with all the control layers. One of my particular favorites is the mega panel right now, right? The rain screen assembly where everything is in a plane of its own, where we can try to keep things where they belong and continuous where they belong, particularly at joints. And, there's particularly in panelization, you have to be very cognizant of the joint detailing, right? That four-way panel joint. You can't just smoosh gaskets together and expect to get a passive house level of air tightness. So comes down to a lot of the detailing and coordination with fabricators about what's possible. And there needs to be some further innovation in the market of products. And we're having some conversations with fabricators right now about different solutions that may need to become more prevalent. Other panelized systems, not so good from a thermal standpoint. Unitized curtain wall, probably not gonna get there with the backstop with a lot of unitized curtain wall. Precast has its own challenges. Higher embodied carbon, maybe not something you wanna apply to a building that's striving to achieve low operational carbon. So lots of considerations there, and it's definitely a challenge.
I think we had a question, yes.
The industry's been moving towards performance-based code requirements for some time. One of the biggest challenges has always been because those requirements can be unique project by project. And because of that variability, one of the things is always it's hard to validate up front until everything's complete, because then you're doing like a whole building air tightness test. So for instance, if a project is claiming a whole building air tightness of 0.15, in order to be able to hit its target, its TEDI values, and then the whole building air tightness is performed, and it comes back at 0.38. What then?
Yeah, I mean, you would have, if you want to rely on air tightness to achieve your goals, you have to deliver. And Passive House now has shown us that they've literally built tens of thousands of projects that achieve 0.08. So, those kind of levels are totally achievable.
So again, it comes down to really careful enclosure detailing throughout the process, making sure those are built and coordinated. And then, on site, you don't have to wait till the final air tightness test either. What's really common in Passive House as well, or some intermittent tests prior to the final, just to make sure you're on track. Potentially, when the building is airtight, your AVB's in place, your windows in, perhaps your interior finishes are not in yet, things are roughed in, but you have a chance. If it's panelized, obviously it's varying degrees of exterior things may be in place, but maybe you're at a point where you have access to the air barrier as well. Running intermittent tests along the way is another way to safeguard against passing the final, and taking steps to mitigate any air tightness issues through CA before that final test is ideal. So careful detailing and then careful field observation has a proven track record in places like Passive House.
Yeah, good question. I think we had a question there, yes.
Yeah, in your case study, you showed 6 inches of 6-inch thick mineral wall insulation, which is now becoming fairly common, or certainly 5 inches is and 6 inches in some cases. Are you envisioning that 2 years from now we're going to see in a cavity wall or ring screen wall 8 inches of mineral wall insulation, or like where do we see it going with this?
Yeah, that's a good question.
Well, again,
Andrew.
it's a balance.
Sell mineral wall, I'm just asking.
The guy behind you does. Yeah.
12 inches.
Yeah. Well, again, it depends on how you balance the energy budget. What's the form factor of the building? If it's a really poorly performing form factor, you're gonna have to rely on much higher R values. So it depends on how you balance the whole energy budget with those key levers through the design. So it's a holistic design process. And yeah, if you wanna, do a really skinny hot dog building, maybe you need to jack up the R values a bit. So, depends on the energy modeling. That's why we do the energy model early, to figure out early what we need to buy for that wall or roof or whatever.
Yeah, that's a good point. I just wanted to talk about the form factor for a second, because I don't want to get in, I don't want anyone to have the impression that certain forms aren't buildable with the Teddy and
No,
things.
it's just trade-offs.
It's just a matter of like, you have to compensate somewhere. We did. When we were developing the Teddy limits, we literally did hundreds of permutations of form factors and whoosies and whatsies. And so we found that, you know, the Teddy limits can be achieved and whatnot. It's just that you sometimes have to compensate in other ways. That's why we're saying like, you guys need to be involved from go. Because if there's a weird form factor issue, then you're gonna be like, okay, then we gotta pay attention to these other levers more than we might otherwise, that kind of thing. Okay. Let's get any new question people. Yes, ma'am.
I'm just thinking about the buildings and see what all you guys, what do you think in the future when those buildings need to have maintenance done to them, what's gonna happen to those buildings?
Well, the real question is what happens when Birdo kicks up a notch. There'll be some retrofits in the future. But what you
I'm sorry, I didn't like hear the whole question well.
Just thinking like maintenance, if buildings eventually need maintenance, obviously those buildings, the unitized buildings in the seaport, big unitized buildings have gone up as many of them. Like what's gonna happen to them in the future? Is there gonna be like deferred maintenance on them? Like eventually they're gonna have some work done to them. And they're not gonna meet the standards.
Oh, you mean with Birdo making it, with increasing the declining, how would you say it, the penalties that will be coming? Yeah, that's a good question. I mean, that's you know, the code doesn't have declining anything. Like the code that you build today, you know, you pass the code and you're done. I mean, the code doesn't make you like get harder and harder to build or harder and harder to achieve things as time goes by for a building that's already built. So yeah, I mean that, but for the standards that are coming that are the Birdo type standards, that's a good question. But I would, in terms of maintenance, I did, you know, I would want to pitch again here that building enclosures, that's the way to go for strategies. I think we built way too many buildings in the past decades where for enclosures and then HVAC systems forgive all sins. And if you want a building that's high maintenance, that's the building. It's got the most moving parts, got parts that break, you know, on and on. Yeah, if I'm an investor, what do I want to spend my money on? I want to spend my money on a thing that doesn't move. So building enclosure is one of those things. And what do I get at the end? I have a building that is more resilient and more comfortable as well. So do I want to put my money into a fan? Or do I want to put my money into a wall where I don't hear the outside and I feel comfortable sitting right next to it? So think about those things as you're thinking about this sort of transition to building enclosure oriented development. That's really the pitch for your, you know, for your developer clients. That's I think it's a better direction for everyone from that perspective too.
Should we grab an online question too here?
Oh, yeah.
Yeah.
How do we do
Come
that?
back. I'll read it off.
Okay.
Can you discuss the definition of glazed wall? Does a glazed wall need to include both spandrel area and fenestration area, or does it need to contain either spandrel or fenestration? When does a window wall become a glazed wall? Well, there actually is a definition of glazed wall system in the definitions.
Yeah.
I mean, we could find that and read it.
Well, the basic question there is the glaze. So we're used to window to wall ratio, right?
Mhm.
So which is kind of a misnomer. It should just be called aperture percent. Because it's not actually a ratio of windows and walls. It's a ratio of windows and total vertical, right? So that's window to wall ratio, again, should be called window to total vertical ratio. So glazed wall percent is the amount of glazed wall system, which includes both the opaque portion, spandrel portion, as well as the vision portion. So it is not meant to be a percent of vision. It's a percent of how much of your overall vertical is that kind of system that is both opaque and vision. So our code is actually calling out glazed wall systems separately because we think they deserve to be, we need to have a way to treat them And we actually give them kind of if you have a large glazed wall system, we lower our standards. Because we wanted to make sure that glazed wall systems have a shot at being continued to be used. So that's why that is like that. Hopefully that answers the question.
Yeah, I mean, in short as well, I mean, the glazed wall is an NFRC term, which was incorporated here as well. So it includes vision glazing and spandrel, as you said, whether that is glass
Mhm.
or opaque, metal panel, back pan, or anything glazed into that system is considered that glazed wall.
Yes.
And is subject to, well, actually, all above grade wall is subject to the backstop. But within that, specifically, the vision glazing has a limit of U 0.25
Mhm.
whole window, including for operable.
Correct.
If I recall correctly, average per elevation, right?
Correct.
Okay.
And yeah, so there is in fact two backstops when you talk about glazed wall systems. So we have the overall UA backstop to make sure that we get at least that. And then if you're using a glazed wall system, then we have an additional backstop that the vision portion is 0.25 or better. And we do have an accommodation that we've written in now for 0.3. So that will be released in the guidelines that will come out in a couple of weeks. So 0.25 left 0.3. The reason for that is because this has to do with thermal bridging. Because glazed wall systems, the opaque portions of glazed wall systems, even if you have R30 in that opaque portion, that's going to have an effective R that's going to be like R6, R8. If you're really good, it's R10. So we actually assume that you're really good. And, assuming that that's no higher than R10, you would need 0.25 in your window in order to achieve the overall UA. That's where that comes from. And if we didn't have that 0.25 backstop to the backstop, what would happen, and what we've seen happen because we review lots of projects, is that people will have the opaque portion and they'll say that's R18, it's R20. And therefore my window, I'm going to be able to do a very low performing window, and my overall average is going to be achieve the UA. And that's very counterproductive to what we're trying to do. So it's just recognizing that there's a lot of thermal bridging in a system that's made out of metal and glass. That's the fundamental problem with glazed wall systems. So we're recognizing that, and we're giving a lot of we're making it as easy as possible here, because we're saying you can get as good as R10. That's actually kind of hard to do. And then if you're above 50% glazed wall system, actually lower the overall UA standard. So we're put a number of accommodations in there to try to make glazed wall systems work, because we know how popular they are with electronics.
A similar online question: is there a way to design using prescriptive values on buildings that have a low window to wall ratio, like 20%? So i.e. prescriptive for fenestration.
Yes, so if your building's under 20,000 square feet, straight up prescriptive all through, no modeling and things. If your building is petty or ashray traffic, it's more than 20,000 square feet. I'm trying to remember now what it requires. If you're under 30%, well, you still have to show that you're achieving all of the thermal bridge derating, et cetera. So yeah, there isn't an R value table anymore to just go to and say I have R 7 plus R3 CI, like that doesn't exist. I'm not sure if that was the question. So that's gone. Because we can't have a table like that and do derating and have that make sense. So that table's gone. We just have to achieve a U after derating. So hopefully that answers the question. If I'm not answering your question, just call me and we can have a phone call. Any other questions from here?
Yeah, 6 months.
Come back to, yes, sir.
So the BEC Hydro Guide is a great tool. I imagine more are gonna be developed, and there are already some out there that may have models that the BEC hydro guide doesn't have. But that guide is the one that's explicit stated in the code. How can we use other guides? Or how do we know which guides would be accepted to use? There's a model in there that we can use.
I haven't seen kind of as thorough a database like BC Hydro. If there was one, we could consider adding that to the, to the list that you can go to. So if something like that emerges, let us know and let's look at adding that in. The reason there does have to be, it has to be well done. BC Hydro's all three-dimensional models, it's extremely high level of quality assurance. So that becomes kind of a good go-to. If there's other databases that emerge, then we're interested in them. There would also have to be a high level of quality assurance. Yeah.
The third option allows for manufacturer-specific thermal model.
Well, it depends. So if you have a glazed wall system manufacturer and it's two-dimensional modeling, that's not allowed in the code.
Right. But if you're doing cladding attachment, thermally broken, you have a manufacturer that's done 3D thermal modeling with the same engineering firm that did the BC Hydro study, presumably that's an acceptable solution.
Yeah, that would be like the pathway in the code that allows you to model. So yeah, it's just a model that someone has already finished for you. Yeah, that's for sure.
Right, again, like a lot of the product data for like night wall, has that already, right? Yep.
Any more internet?
Well, there's many more internet.
Oh, we're over time. What do people want to do about time?
You go.
I can stay as long as people like. I don't know about Andrew.
I'm,
Yeah, okay, let's keep going.
let's see. Oh, okay, interesting. There are architects, envelope consultants that exist mostly in the existing construction world. Haven't touched on that yet. Rules of thumb for window replacements in existing commercial buildings, large condos, please. Assume brick with punch windows. Yeah, we didn't really talk a lot about the existing buildings, but that's chapter 5 as a whole piece of its own. So. thoughts on that?
So, yeah, so let's go over that. So we actually didn't change the way the IECC rules work much. All we did was just show you which sections to go to. But the rules in IECC are as follows. If you're not changing use, so if you have an office building and you're upgrading it to an office building, then that's an alteration. And the rules say that if you touch it, you upgrade it to the current code. So if you're not touching the walls, if you're just putting in new windows and HVAC system, then you leave the walls untouched. And you have the windows and the HVAC system comply with current Dutch code. Now that's alterations. So that the energy code doesn't make you chase out stuff that you're not planning to touch. Okay? Now it's different if it's a change of use. And I didn't write this rule. This is what IECC says. Change of use says that if I have an office building and I change the use, so now I have a condo, it says that now I do have to chase everything out and bring it all up to code. That's what the rules are. We didn't write them. So those rules that's just the way they are now. So it is very draconian, but it is draconian because it needs to be. I mean, if I have an old office building and I convert it to condos, we don't want to have, very low performing walls with condos and things. It's going to cause problems, right? So that's the way all the existing buildings code exists now. Those are the two pathways. So, I'm sorry?
What about additions?
Oh, additions, thank you. So yeah, the other thing is an addition. If my addition, I have an existing building and I put an addition on it. If my addition is less than 20,000 square feet and not doubling the size of the existing building, then it's a small addition. It's just treated like new construction prescriptively. Just the addition. You don't have to do anything to the existing building. Okay, if I'm putting in new windows in the existing building, then I treat the existing building like an alteration. So you can mix and match as needed. If your addition is large, more than 20,000 square feet or more than doubling size of the building, then it's treated like new construction, including TEDI pathways, ASHRAE pathways, etc.
Okay, so in the case of small addition less than 20,000 square feet, prescriptive, but still complying with the backstop.
Oh, yeah, backstop's always,
That's.
always compliant in the thermal bridging.
And in the example where you mentioned you're just replacing windows but not touching the wall, subject to backstop there.
No, there's nothing to do with the walls then. Just put in the prescriptive, 0.3 window or whatever.
Right, because there actually is a fenestration value table still in the code.
There's a fenestration you guys saw.
And you're allowed to follow that even if the alteration is over 20,000 square feet.
The 20,000 square feet has nothing to do with alterations. That's
Okay.
just additions. Alterations of any size. That's the rules, yeah. And we are discussing internally creating kind of an alterations. I don't want to call it code, but an alterations, acceptable alterations, if you will. I should say acceptable change of uses. So is there a way we can do more lean change of uses where we don't have the draconian requirements that IECC requires? So I'd love to do that. I feel like for a lot of building uses, a lot of scenarios, it's probably good enough to have high quality windows, low air infiltration, and high level of ventilation coverage without necessarily, increasing the U value of the wall. So there's probably combinations that work quite well, but not currently allowed by the code. But we are interested in doing something like that in the coming year or two. So if anyone's interested in that, reach out to me and we'll get you involved in helping us write that.
And as you started to mention, change of occupancy in addition to additions and alterations has its own set of requirements. Like you said, again, converting a formerly commercial building to residential, that enclosure is now subject to
It's
all the same new construction.
treated like new
Requirements,
construction. Yep. There's still a historic building exception that's unchanged. So if your building is on a historic register, you can apply to the authority having jurisdiction if you can demonstrate that it's like way too hard to do a particular thing in the code because it would ruin the historic structure of the building, then you can get exempted from that. So that still exists. And that might apply to some of these old libraries and things.
Follow-up question on existing buildings. Isn't it change of use plus increase in energy that triggers full compliance?
Just discussing that today. I think so. If you have a particular examples, reach out to me because it gets, the change of use. The words say a change of use which increases the energy use. Yes, I would say that that's a true statement. You kind of have to have both things for to have to follow those rules.
So if it's a change of use that doesn't increase.
Yeah, I couldn't think of an example that happens, but maybe you have that. I'd like to learn about that and let's make sure that we're on the same.
You're really only got one question there.
27 total.
Maybe we just do our closing remarks, but you guys are hanging out to keep answering questions.
Yeah,
Sure.
absolutely.
That's my time to sit down next time.
Yeah.
Thank you all so much for coming out here and thank you to presenters, if they kind of. Last slide with the learning units.
Yes.
So anybody who needs learning units, AA credits, just scan the QR code that they put up here. You can get that. Big thanks again to Glazing, specifically John Myers for setting this up. A lot of great events coming up. We have again the COTE event coming up next Friday, June 16th, 9 a.m. We have Facades Plus coming in July 12th, and then BEC events on panelization July 19th. I'm sure they have a lot of fun things to say about the stretch code and how this will impact them going forward. But again, thank you for everyone coming out, Gilbane and presenters again. So everyone have a good night, and they'll hang out to answer more questions. So thank you.